Okay, let me start over again. So again, we're in section 15.5, talking about molecular structure and the strength of acids. So going down a group, so group 17, the halogens, right? Hydroiodic is the strongest, and the acids get progressively weaker as we get down to hydrofluoric acid. So why is this? Okay, remember what an acid is. It's a proton donor. So what determines the strength of an acid is how easily the molecule can get rid of its proton. So why is this stronger than this? Well, going down a group, the factor that determines how easily an acid can get rid of its proton is the size of the counterion, the anion. Iodine is a much bigger atom than fluorine is, and the sizes of the atoms get progressively smaller as we go to the left here. In other words, going down a group. The bigger the atom is, the less it's going to be able to hang on to that proton, right? So because the proton is much further away from the nucleus of the iodine atom. So the bigger the atom, the easier it's going to be to get rid of the proton. In addition, the electronegativity is strongest here and smallest there. Remember what electronegativity is, the ability to attract a pair of bonding electrons. So the fluorine is going to attract this proton more than this is, right? But primarily its size is the dominant factor. Size is the dominant factor. How about going across a group, right? Across a period, I mean. So they give us the example of water is much weaker acid than hydrofluoric acid is. All right, now why is that? Now, when you're going across a group, across a period, the sizes of the atoms, they get progressively smaller as you go from left to right across a period, right? But from one element to the next, the sizes are all roughly the same. So the size factor that affects down a group does not really come into play going across a period. So what is the dominant factor here? The dominant factor here is the electronegativity. Remember that, so I mean, this guy pulls the bonding electrons towards it, so the proton is not doesn't have as good a share of the electrons here as it does here. Let's see, what else can we say here? Oh, yes, I forgot, bond polarity. So here the electrons are pulled much closer to the fluorine atom, and again, that's due to fluorine having a greater electronegativity. So this is a much more polar bond than this guy is. So if the electrons, here, if we draw this like this, right, and the hydrogen atom is here, right? So the hydrogen, so this is a bare proton sitting out here. The electrons, the bonding electrons are pulled towards the fluorine. So this proton can much more easily be pulled away from the fluorine, okay? Because it doesn't have as great a share of the electrons as it does perhaps in water. So here, the electrons, oxygen's is not as electronegative as fluorine. So the electrons are not pulled as close to the oxygen as they are in hydrofluoric acid. So the proton here actually has a little bit of share of these bonding electrons. So it's going to be a little harder to pull this proton off than it is to pull this proton off, right? Again, the book talks about it in terms of bond polarity, but again, that bond polarity is determined by the electronegativity of the hetero atom, right? So to summarize, going down a group, the acids get stronger. Going across a period, the acids get progressively stronger. Okay, how about the oxyacids, right? So this is the HOY that they're talking about here. Okay, so, and actually I'm not going to draw this up on the board, it's right there in our book. So they use the two examples, hypochloric acid and hypobromic acid, bromous acid. again, the HCl, the chlorine atom is more electronegative than bromine is. So notice in these oxyacids, the proton, that's the acidic proton, is attached directly to an oxygen, right? And then we have another heteroatom Y, HOY. Here, let's draw this up on the board here, even though I just said I wouldn't. So again, there's the acidic proton. It's always attached to an oxygen in these oxyacids. And then the oxygen is attached to another heteroatom. The more, now we know oxygen is rather electronegative, right? The second most electronegative. But so the protons are pulled towards the oxygen here. But if this is a highly electronegative atom, they're going to be pulled even more towards the oxygen, right? So this electronegativity, the electronegativity of Y can affect how much this bonding pair of electrons here is pulled in that direction. Chlorine is more electronegative than bromine, so HOCl will be stronger acid than HOBr. Okay, and again, it's simply the electronegativity of Y that determines this hierarchy of acidic strength here. If we had we could add HOI here, and that would be even weaker than this, because again, iodine is less electronegative than bromine is. Okay, any questions there? Any questions? All right, how about, let's see here. Okay, so there's one more here on the next page, 533. And they show us that so this won't take very long. Well, let's see, they write them in, let's write it in the order they write it. It's weaker than HClO2, is weaker than HClO3, is weaker than HClO4. Now, it's unfortunate that they write it like this. Remember, the acidic proton is attached to an oxygen. So here, if we were to write this out, it actually looks like this. Okay, HClO. The bonding is actually in this pattern here. Here, I'm going to add another oxygen. So again, I'm increasing the overall electronegativity in this direction. If I add another oxygen, these bonding electrons here are being pulled even more in this direction. So the more highly substituted the chlorine is with oxygens, the more, here, let's put a different color here. All right, here, let's go back to just this. So the electrons are pulled that way. We have an oxygen and a chlorine. If I put another oxygen here, these electrons are going to get pulled even more in this way, as I'm adding another highly electronegative atom to the chlorine. I add a third oxygen. They get pulled even more than that direction. And fourth, now they get pulled even more in that direction. The more highly substituted this heteroatom is with oxygens, the more the bonding electrons will, between the hydrogen and oxygen, will get pulled towards this oxygen. Okay, the more they're pulled, that means the more easily it is to remove this proton from this molecule. So the more oxygens, the stronger the acid. The fewer the oxygens, the weaker the acid. Does that make sense? Notice that in every one of these cases, we had 3 or 4 different cases there. It was always electronegativity played the major role, with the exception of going down a group. Right, going down a group, it's the size of the heteroatom, the atom that the proton is bonded to. That was the determining factor of how strong the acid is. In the oxyacids, it's the greater the electronegativity of this, the stronger the acid. And the more highly substituted that this heteroatom is with oxygens, the stronger the acid becomes. Okay, so again, it's all how much these electrons are pulled away from the hydrogen. Okay, any question there? Any question? All right, so that's it for that chapter. All right, that's it for that chapter. All right. So now we're in the chapter on weak acids and bases. Weak acids and bases. So here we're going to use that. Geez, I wish I had a podium here. Let me just turn to chapter 16 here. And we will do our little lab today. So I hope you are ready for that. Okay, so we have this chapter 16. And I think I asked you to start reading the first couple sections of this chapter. Okay, so we're looking at weak acids and bases. And by definition, a weak acid is one that does not completely ionize in water. So it's an equilibrium situation. All right, so here's the conjugate base. All right. So again, since this is a weak acid, it does not go completely in that direction. Okay, so it's an equilibrium situation. So we should be able to write an equilibrium constant for this process. So how could we write an equilibrium constant here? So the acid dissociation constant, so instead of using Kc, we're going to use Ka for acid. Simply equal to products over reactants. And remember, we leave out the H2O. Okay, so there's the equilibrium constant for the dissociation of a weak acid. Okay. Let's see here. So let's take a look at actually, I just want to, just a bit of terminology here. On page 545, under this little section on experimental determination of Ka, I just want to talk about this term degree of ionization. Okay, and the degree of ionization is the fraction of molecules that react with water to give ions. Okay, so for our purposes, we could calculate it from this acid dissociation reaction here. We could calculate the degree of ionization as just this concentration of hydronium ion divided by the starting concentration of this, not the final, not the equilibrium concentration, the starting concentration before equilibrium sets in. Okay, so again, it's the equilibrium concentration of H3O plus or A minus for that matter, it doesn't really matter, divided by the starting concentration of the weak acid is the degree of ionization. And if quite often that will be expressed as percent ionization. So you would just take the degree ionization and multiply that times 100% to get the percent ionization. I usually like to phrase it in terms of percent ionization, right? And if I remember correctly, the first problem or two here, we're asked to calculate the degree of ionization here. So let's take a look at section 6, example 16.1. Again, I'm not going to work the example. We'll work the exercise. So let's take a look. So we're determining the equilibrium constant from the pH of the solution here. So we're given exercise 16.1. Let me erase the board here. Somehow I'm going to have to figure out a way to, I don't have to hold this book in my hands. Okay, so we have lactic acid is found in sour milk, and we have a 0.025 molar solution of lactic acid that has a pH of 2.75. What is the equilibrium constant? and what is the degree of ionization. Okay, so the starting concentration of, I'm going to call it HA. All right, so is 0.025 molar. Okay, and the pH is 2.75. Hopefully that's an M there, 0.025 molar. All right, and we're asked to find Ka, we don't know. And we're asked to find the degree of ionization. Okay, so let's write out remember, you should remember this general form for any the dissociation of any weak acid in water. It's always going to be the same. So actually, rather than writing the formula for lactic acid, I'm just writing A. All right, A. So this A minus would be lactate amine. When it's protonated, it's lactic acid. Right? That saves you from having to write out the formula for the acid in each case. So we can write an equilibrium acid ionization constant for this. So Ka is equal to H3O plus times A minus divided by HA. Okay? Now, we can get the equilibrium constant, from the pH, we can get the hydronium ion concentration. We learned how to do that in the last chapter, last class. So let's go ahead and do that. All right, I'm going to bring up a different board here. Everybody remember how to calculate the hydronium ion concentration from the pH. All right, the hydronium ion concentration is equal to 10 to the negative pH. All right, we learned that last class. So 10 to the negative 2.75 is equal to, so 2.75 negative second 10x, and I'll put that into scientific notation, is 1.778 times 10 to the negative third molar. Okay? All right, everybody with us? Everybody with us? Okay, yes. So now we know that. Okay? Everybody have that written down? Okay. Yeah. So what we need to do here, actually, I guess I prematurely set this up. We should make an ice table here. All right, so at the beginning, this is 0.025 molar. This is 0, this is 0. So ICE. The change in this is going to be minus X. This will be plus X. This will be plus X. So at equilibrium, this is going to be 0.025 minus X. This will be plus X. This will be plus X. Okay? So now we know what this X is. We just calculated that. Right? So we know this number and this number. You can easily get this number, 0.025 minus that number that we just calculated. So again, I'm going to write Ka. Sorry, I prematurely wrote this up here before. Actually, I'm going to erase this ice table because I'm going to run out of room. You guys have this ice table? Okay. Yeah. So I'm going to erase this. All right, and Ka, there is going to be one problem working these problems. These problems can get a little long in this chapter. And I only have this small board to work with. Actually, I have 2 more of them out in my car. Maybe I can grab those and use those also. All right, so from the ice table, I know the equilibrium concentrations. X times times, or divided by 0.025 minus X. Right? That's what it was? Yes. Right? I know what X is, so I can calculate Ka. So Ka is equal to, what was it? 1.778 times 10 to the minus third. And that's actually going to be squared, but I'm going to write, actually, here, let me write it in a different color. Because I'm kind of writing them close together because I'm going to run out of room here. So I'm going to write a different color so that you can spot the different lines. It's 10 to the minus third molar and 1.778 times 10 to the minus third divided by 0.025 minus 1.778 times 10 to the minus third. Okay, and all we got to do is get a calculator out. Now I'm going to do this denominator first and put that into memory. All right. Oh, I just erased that number. I had it on. So 0.025 minus 1.778. 0.025 minus 1.778 double E3 negative minus, what's going on here? 0.025 minus 778 double E3 negative equals stow 1. Okay, now, so I have this denominator in my first memory. All right, so 1.778 double E3 negative squared divided by recall 1 equals, and I get 1.36 times 10 to the negative fourth. All right.
Quick question.
Yes.
So when I'm looking at it, your A is gonna be equal to your H3O. Is that what you're writing on the?
Yes, because if you look up here, for every one of these, I get one of these, right?
Oh, okay.
And the coefficients are both 1.
Oh, okay. But if they weren't 1, it would.
Right. So if it's for these weak acids, it's almost always they're going to both be 1. They're going to both be 1. Because even if you have a polypronic acid like H2SO4 that has 2 acidic protons, you got to calculate the it's stepwise. Okay. So here, let me do it on this one, just so you can see what I'm talking about. That's actually a good question, though. So you can see what I'm talking about here. And we'll have these polypronic acids later in the chapter. So if I have H2SO4, all right, plus H2O gives me HSO4 negative plus H3O plus. They don't both, so you got to write an equilibrium constant for this, and then you have to write an equilibrium constant for this. Okay, you have to treat it as 2 separate problems. You can't just take both protons off at once. Okay, does that make sense?
Yeah.
Okay. So let's see. So now we have, I'm going to put that into memory there. All right. So there's my Ka. Did anybody check it? There's actually a table of acid dissociation constants on the next page, but unfortunately, lactic acid is not one of them. So I'm looking at, in the back of the book, they have 1.4 times 10 to the negative fourth. And I did go 1 decimal point too much. I realized that at the beginning, because they told us this initial concentration is only 0.025, so I can only have 2 significant digits here, right? I can only have 2 here, so that really should be 1.4, right? Just like here, this should have been 1.8. Okay, but that's okay. We still have to calculate the degree ionization. Does anybody have any questions here so far? Okay,
No.
Let's just review one last time, because you're going to do this many, many times. What we did, we wrote out an equilibrium expression for the acid dissociation, right? And that's going to be the same for every one of these weak acids. The molecular weak acid reacts with water, give us hydronium ion and the conjugate base. Set up an equilibrium constant expression, leave out the bulk water, because there's so much more of that than anything else. We learned that in the last chapter, right? Set that up. Have this written out. We set up the ice table, and we had the equilibrium expression for this, this, and this. Next step, we just substitute in the values from the ice table, from the last line of the ice table. But from the pH, we were able to figure out what the hydronium ion concentration is, right? Again, that expression, hydronium ion concentration equals 10 to the negative pH. You remember that equation. You're going to need that quite often. Okay, so that's how we figured out what this X is. From the ice table, I already erased it. Remember, we saw that the equilibrium concentration of hydronium ion equals the equilibrium concentration of the conjugate lactate base. Okay, so we set those two equal. We knew what X was here from the ice table. Just plug in for X and solve. Right, so rather straightforward there. Okay, all right, now we're going to need, we still have to calculate the degree of ionization. So let's write an equation for that. So again, I usually like to write it percent ionization, but they're calling it degree ionization equals H3O. Actually, let's not call it that. Let's call it A minus. They're the same in this problem, but they won't always be. At equilibrium, right? So the concentration of the conjugate base, which is the same as the hydronium ion concentration in this problem, divided by the starting concentration. So I'm writing a 0 here. It's not at equilibrium, at the starting concentration. So that was and if I remember correctly, this was 1.778 times 10 to the negative, what number was that? The exponent?
4.
4. So we should get.
I thought it was -3.
I have -3 also.
3? Yeah, on the equilibrium constant, it was 4. So 1.778 times 10 to the third negative divided by 0.025 equals 0.071, which is what's in the back of the book. Okay? So we see how to get the degree of ionization. Remember, this is at the beginning, not equilibrium. Right? Not equilibrium. Right? And again, if we wanted percent ionization, we would just take this equation, multiply it times 100%, would give us percent ionization rather than degree ionization. Okay? Are we good here? Any question on the whole problem here? Any question?
No.
Again, quite often, there's always going to be like some hidden quantities in these problems with the weak acids. Like in this one, it was that you were, from the pH, you were able to get the equilibrium hydronium ion concentration, right? You're just going to have to recognize when you can do things like that, okay? So like when you set up that ice table and you see a plus X for the hydronium ion concentration, And it's like, okay, where am I going to get this from? This is why we write stuff down over here, because you only have this information, two pieces of information given to you in the problem. From one of them, you're going to have to get the hydronium ion concentration. Obviously, you're not going to get it from that, so it has to be from that. Okay? This is why we write what's given to us on the right-hand side. Okay. Let's see here. So we have this big table for ionization constants here on page 547. You should be aware, if I remember correctly, for a lot of problems, you're going to have to refer back to this table. They're not going to tell you find the Ka for a particular acid in this table. They're just going to expect you to know that. Okay, if I remember correctly, there's a much bigger version of this table in the appendices at the end of the book. Okay, so let's see here, calculations with Ka. So once you know Ka for HA for a particular acid, you can calculate the equilibrium concentrations of all of the species in solution. Okay, let's see. So let's take a look at, we're going to do something similar to what we just did, but we're going to use an approximation method here in this particular problem. And this approximation method is very, very useful because it's going to save you from having to use the quadratic equation. All right, so it's important that we get through one of these and see when you can use this approximation method and when you cannot. Okay, so let's have a look here. Working problems with the quadratic equation. I will not intentionally give you any problems with that. I didn't in the last chapter, or 2 chapters ago when we were doing equilibrium constants. I mean, they're workable. They're very, very tedious to do, and it's very easy to make a mistake when you have to plug stuff into that quadratic equation. But we should all be able to do that. Okay, so let's take a look at this. What are the concentrations? So we're doing exercise 16.2 here. Okay, again, you can go through the example yourself. Okay, so what are the concentrations of hydrogen ion and acetate ion in a solution of 0.1 molar acetic acid? What's the pH? What's the degree of ionization? Okay, now here, they do tell us in this problem, look at that table on the previous page for the value of Ka. Right, so let's see, 0.1 molar acetic acid. Again, I'm just going to write KHA. Right, is 0. What was it? 10 molar. All right, and so we should get Ka. Now I'm going to write Ka very small here because I want to have a lot of room to work. So this is acetic acid. So it's 1.7 times 10 to the negative 6. Okay, and we are asked to find hydronium ion concentration and acetate. So we're asked to find 4 things: the concentrations of the 2 products, the pH, and the degree of ionization. So we're going to begin, as always, by writing now and the acid dissociation reaction. So HA plus H2O gives us a double-headed arrow, H3O plus A minus. Okay, and we're going to make an ice table. All right, so this starts out as 0.10, 0 and 0. Okay, so the change here is going to be minus X, this is going to be plus X, this is going to be plus X. For a lot of these problems, the ice table is going to be almost the exact same in every problem. At equilibrium, this is going to be, okay, so we good there. All right, now I'm going to erase this here because I'm going to need this room to work. Okay, but now we have the ice table. All right. All right, so let me erase this. So you guys should have that all written down. And we're going to write an expression for Ka, which is H3O plus times A minus over HA. All right, now, where am I going to get the equilibrium values from? From the ice table. This is not an equilibrium concentration. That's why I put that 0 there. And you should do that also so that you don't get confused. Right, so we're going to get all these values from the ice table. Right, so Ka is equal to X times X divided by 0.10 minus X. Okay, now, this is going to be a quadratic equation, X times X squared, and I'm going to have an X term on this side, right? If I bring this over to here, right, that's going to give me a quadratic equation. I have an X squared term here and an X term here. We're going to make an approximation here. We're going to say that this is very small compared to this, right? So I'm going to write on the next line, Ka is approximately X squared, all right, multiplying those two together, divided by 0.10. Okay, and we'll find out at the end whether or not that approximation is valid. So now all I got to do is solve for X. I bring this over to the other side. 0.10 times Ka is approximately, notice I got rid of the equal sign now because we made this approximation here, is approximately X squared. Okay, and I always like to put the unknown on the left-hand side. So X is approximately equal to 0.10, I'm just flipping sides here, times Ka. All right, and we're going to take the square root of that. Remember, raising to a power of 1/2 is the same as taking the square root. Okay, so X is approximately, now we're going to plug in the value for Ka here. 0.10. Can everyone see the bottom here as I'm writing? Everybody can see that?
Yes.
Yeah.
Okay, 0.10 times Ka. There's my Ka right there. That's why we write that stuff on the right-hand side. Times 10 to the -5th, and then the square root. And I'm going to bring it up here. All right, so now I get out my calculator. So 0.1 times 1.7 times 10 to the 5th negative equals square root. Right, and I get X is approximately, I'm going to put it into scientific notation, 1.3 times 10 to the -3rd molar. Okay? Now, that's my hydronium ion concentration. All right, so where do my different color? Oh, I guess some of them are over there. So we were asked to find 4 things. The hydronium ion concentration, which is X. The concentration of the conjugate base, acetate, which is X. Now I'm going to write that down here. H3O plus at equilibrium equals the concentration of acetate anion at equilibrium, which is equal to 1.3 times 10 to the -3rd molar. All right, and let's check in the back of the book, make sure that that's the right answer. Yes, it is. Okay, it's a pretty straightforward problem. Okay, we're still asked to find 2 other things here, which was the pH and the degree or percent ionization, degree of ionization. Well, let's find the pH first, because we have the hydronium ion concentration right there. pH equals negative log of hydronium ion concentration. You got to know this formula here. So pH equals negative log of 1.3 times 10 to the negative 3. Right? pH equals negative log. So I get my calculator out. I have this sitting on the screen right now. And I'm going to put that number into memory. Right? This number. I have it on my screen. I'm going to put it into memory because we're going to need it for the degree of ionization. So store 1. So that negative log. So recall 1 log negative. And I get 2.9 equals 2.9. Okay. And oh, actually, wait a second. We should go with the 2.88. Here's why. I'm just remembering from last class. This is what they have in the back of the book. If you remember from last class, when we learned to calculate pH, they told us that the number of decimal digits should equal the number of digits you have here in the hydronium ion concentration. So I have 2 significant digits here. I should have 2 after the decimal here. I won't mark you wrong for that though. Right? But that was one of the things they told us in the last chapter, if you remember correctly. Okay, so 2.88 is the pH. We have to do one more thing, which is calculate the degree of ionization. Right? The degree of ionization. All right, any questions here so far? Any questions? Now, the degree of ionization is just going to be H3O plus equilibrium concentration divided by the starting concentration of the acetic acid. Okay, so I'm going to switch to the other board for that, in case somebody might have a question on this big board. Don't want to erase it yet. Okay, so degree of ionization. I'm just going to put DOI instead of writing it out every time. Equals H3O plus at equilibrium divided by the starting concentration of acetic acid. All right, well, we know what that is. Right there, 1.3 times 10 to the negative 3rd is the starting concentration of equilibrium concentration of hydronium ion. And right there, again, that's why we write it on the right-hand side, is the initial concentration of the free acid. All right, so that's, well, we can see what that's going to be, right? That's just going to be 1.3 times 10 to the negative 2nd. Okay, don't even need a calculator for that. Okay. Now, remember, acetic acid is the acid in vinegar. So in a bottle of vinegar, this is roughly the degree of ionization in a bottle of vinegar. All right. Bottle of vinegar, I can't remember what the concentration is of acetic acid, but it's very low. It's probably close to 0.1 molar, right? Probably even lower than that. Okay, so it's not very acidic, but it's still strong enough. When you pop open that, take the lid off a bottle of vinegar, and that pungent aroma you smell is this free acid here, the free acid. Okay, so there's the degree of ionization. Any questions on this? We still haven't done. Can I take the small board down?
Yeah.
Okay. All right, so we still haven't justified this approximation right here, going from this line to the line in pink, dropping the minus X. How do I know when I can do that? And if we look on page 549. They tell us there. This is a very useful thing. Okay, so in italics there, the last full paragraph. How do you know when you can use the simplifying assumption where you neglected x in the denominator of the equilibrium equation? How do we know when we can do that? So the next line in parentheses tells us when we can do that. It can be shown, although they don't show us, that this simplifying approximation gives an error of less than 5%, okay, if the concentration of the acid Ca, that's the starting concentration, all right, 0.1 molar in this case, divided by Ka, the starting concentration divided by Ka equals 100 or more, equals 100 or more. So let's calculate that. I'm going to do it on the small board here. So if you're working a problem, you should always check this. If the starting concentration of the free acid divided by Ka, if that's bigger than 100, you're justified in dropping this X here. All right, so let's plug in here. 0.10 divided by 1.7 is going to be way bigger than 100 equals, let's get out the calculator. So 0.1 divided by 1.7 is 10 to the 5th negative equals, and I get 5.9 times 10 to the 3rd. So almost 6,000, right? Almost 6,000. So way, way bigger than 100. So that tells us this approximation here was, in fact, valid for this particular problem. Okay? Again, always have that in the back of your mind. All right? Always have that. Yeah, here, I'm going to, can I take this small board now? Are we good? Yeah. Okay.
Yeah.
Actually, maybe I should turn chat on. I see there's one message that somebody typed in. Oh, okay. Actually, Liz, that's probably because maybe somebody else in your home is on the internet. When you're doing a Zoom class, that's what I have found. If you notice today, we haven't had one, my internet hasn't gone out once, has it? Since we started today?
It's probably mine on my side. I don't live in a very good service area and my satellite's horrible, so.
Yeah, but since I got rid of my other computer, I'm having far fewer problems. Okay, so let's see, what were we talking about here? Yes, I wanted to point out one other thing here while we're on this page. Okay, so if we take a look at figure 16.3 here, figure 16.3, I used to give my high school students a problem where they had to actually kind of, in essence, reproduce this graph here. It's a variation of percent ionization of a weak acid with the initial concentration, HA naught, of the weak acid. Okay, and so we see it here, and this is generally true for any weak acid. Okay, and we see that as the concentration of the free acid, which is on the x-axis there, as the concentration of the free acid gets bigger, the percent ionization gets smaller. Okay, again, as the concentration of the free acid gets bigger on the x-axis, the percent ionization gets smaller. Right? That's a general trend for any weak acid. Okay, and if you wanted to prove that, well, or at least give an example of it, we have it here for one concentration. We could just change that to, like, I don't know, 0.2 or 0.01 and redo this whole problem and calculate the degree ionization. And we would see if we made it 0.2, the degree ionization will be smaller than what we calculate. If we made it 0.01, it would be bigger. Okay? Any questions about anything so far? Any questions? Again, I'll probably be giving you fewer problems in this chapter simply because they're a little bit longer. Okay? All right. But again, that means you got to be extra careful because, you know, you can make a mistake anywhere in here. Let's see. All right, so let's turn to the next page, example 16.3. So there's an example using the quadratic equation. I'm not going to give you that. Everybody say thank you, Raymond. I'm hearing it. I'm going to have to assign you some problems on that. Come on, let's hear it. Let's hear it. Okay.
Thank you.
All right, you're welcome. You're welcome. See, take advantage of my good nature. Let's look at this concept check on page 551. This is a good question. Okay.
What page did you say?
551. All right, the concept check. So I'm going to write this up here on the board. So let's see what we've learned here. Let's see what we've learned. These concept checks, this is a very good chemistry textbook. I really like this book. All right, so they have a lot of good concept checks. Sometimes I can't even get them all. All right, let's see here. What was that? Oh, the concept check, yes. So we have acetic acid, HC2, H3O2, and we have HNO2 and hydrofluoric and hydrocyanic acid and RAS. So we have equimolar concentration solutions of these guys. Okay, and to answer that question, we have to go and get the Kas back on page 547 in that big table. So hydrocyanic, 4.9 times 10. Hydrocyanic, where was it? I just saw you there. 4.9 times 10 to the negative 10. Okay, acetic acid is 1.7 times 10 to the negative 5. And nitrous acid, 4.5 times 10 to the negative 4th. And finally, hydrofluoric acid, 6.8 times 10 to the negative 4th. 6.8 times 10 to the negative 4th. Now, we have a solution of each of these. They're all the same concentration. Which one, what do we ask, which one has the biggest pH? Yeah, biggest pH to smallest pH. Anybody know? Obviously, the Kas have something to do with that, right? That's the only piece of information that we have for the whole problem. Other than the fact that the concentrations are all the same. We don't even know what those concentrations are. How are we going to do that?
By the smallest exponent? I don't know.
Anybody?
Can we find the H3O and then use the 10 to the negative power?
You're on the right track. Let's write out an expression for Ka. Right? It's the same for every weak acid. Times A minus divided by HA, right? Now, take a look here. Again, you know, this is something I always try to tell my students. Every equation is kind of like a crystal ball. You just kind of have to know how to look at it, right? So if H3O plus is big, Ka will be big. Doesn't that make sense? They're both in the numerator on opposite sides. The bigger this is, the bigger this is. Right? Do we agree on that? Hello?
Yes.
Okay, the bigger H3O is, the bigger this is. So it's going to be, and so, so let's rank them in order of H3O plus. All right, so the biggest H3O plus is going to be this one, right? This one. So this is going to be number 1. That's the biggest number. This is the second biggest number. This is the third biggest one. This is the fourth biggest one, right? Again, because the starting concentrations were all the same, we can say that, all right? The bigger this is, the bigger this is, right? So, and the bigger this is, the bigger the hydronium ion concentration is. But remember that a big hydronium ion concentration gives a small pH, right? pH 1 is a bigger hydronium ion concentration than is pH 6, right? So the bigger, so this is ranked by, hydronium ion concentration, right? This column. This column is going to be ranked by pH. So it's going to be the inverse for the pH. For the pH, this will be 1, this will be 2, this will be 3, and this will be 4. Okay? Because remember, again, the bigger the hydronium ion concentration, the smaller the pH. The smaller is the pH. Okay? Does that make sense at all?
Yes.
You know, again, if you guys don't want to talk, you can go down to this reaction thing down here on the bottom on your Zoom toolbar. There's a thumbs up. So when I ask a question like that, you know, if you don't want to turn your mute off, you can just hit thumbs up, meaning you understand or agree or something. Okay?
Okay.
All right. So do we understand this? Again, I'm going to summarize. This is a good problem. It really is. I'm just going to summarize. You write down the Ka values and you write out this expression. And we see that H3O plus and Ka are directly proportional. So the bigger one is, the bigger the other one is. So we can order them by that. That should be the first thing you do. Order them by hydronium ion concentration. But you know pH is the inverse of hydronium ion concentration. So in other words, the bigger the H3O plus, the smaller the pH. Right? So you put them in reciprocal order here. Okay? Any questions here? Actually, we don't have a whole lot of time left here, but I do want to mention something that I neglected to mention last class. So I'm going to mention it now. All right? And it has to do with the fact that pH is a logarithmic function. Right? And base 10 logarithmic function. So what we can see here is a pH of 1 and a pH of 4. All right? This, so let's write here the hydronium ion concentration. This is going to be 10 to the negative first. This is 10 to the negative fourth. Right? We can put here pH equals 10. This is going to be 10 to the negative 10th. Right? So what we see here is that a difference of 3 units of pH. This guy is 1,000 times more acidic than this guy is. Right? Here we have 9 different units of pH. The difference in hydronium ion concentration, this one is 9-fold more acidic than this, 1 billion times more acidic. And it has to do with the fact that this is a logarithmic function, right? So a pH of 1 is 10 times more acidic than pH 2. pH 1 and 3, that's a difference of 2 pH units. So that's a difference of 10 squared or 100 times more acidic. Okay? So you have to remember that this pH value is the exponent on power of 10. Right? So every difference of 1 unit of pH is a difference of 10 in hydronium ion concentration. A difference of 10. Okay? So why do they use this logarithmic function? Because hydronium ion concentrations in water can be trillions of times different. Right? It's very hard to comprehend these big differences in numbers like that. But we can easily understand differences of 1 in 10 or 2 in 13. Right? But you have to remember, this is a logarithmic function. So anytime where you see tremendous differences in some physical quantity, quite often, that parameter will be expressed logarithmically. So what are some other examples in science where we see tremendous differences in values? Well, one is the energy released during an earthquake, the Richter scale. So like an earthquake that's 8.0 releases 10 times more energy than an earthquake of Richter scale 7, of magnitude 7. Magnitude was the word I'm looking for. So if I had an earthquake of magnitude 8 and an earthquake of magnitude 5, that's 3 powers of 10 difference. 10 to the third is 1,000. This time, this earthquake is 1,000 times more powerful than this one. 1,000 times more powerful, right? Again, so the range in energy released in earthquakes is tremendous, tremendous. So they use this logarithmic scale. Another one is in the brightness of stars, right? Either apparent magnitude, either apparent brightness or absolute brightness. There's tremendous difference in the brightness of stars. So they use a logarithmic scale. The sun, for example, is magnitude like -26, the apparent brightness. The brightest star in the night sky, Sirius, is, other than the sun, well, the sun's not visible at night, is like magnitude -1 or -3 or something like that. Okay? So again, a star of magnitude 8 and a star of magnitude, let's say 4 powers of 10. This guy is 10 to the fourth, or 10,000 times brighter than this one is, right? So you should understand this logarithmic scale here, okay? All right, and let's see, that brings us to 5:12. We only got 3 more minutes left. So there's no point in starting another problem or anything new. So next class on Monday, or Tuesday, you should take a look at the next few sections, polyprotic acids and the bases here, bases. All right, so sections 2 and 3 and maybe into 4. All right, section 16.4 is pH of, or acid-base properties of salt solutions. Okay. Why don't we, is everybody good? Okay, I got to assign you guys some problems here. Let me wash my hands here. Say again?
Oh, I was just saying that I'm good.
Okay, so I'm going to erase this here. One of these days, I'm going to get some of your stuff graded. And, oh man, high school is just taking so much damn time.
AC for everyone. Thank you, Raymond. Everyone say thank you.
What, for not doing the quadratic equation problems? All right, so let's look at the end of chapter 16 here. Well, one thing good for you guys is when I give you a quiz, it's going to be like, you know, take home, so you'll be able to use your book or whatever. All right. I'm going to move my computer here just so I can have some room to write. Or put my book down, I meant. So let's look at, I want you to do, so chapter 16, I want you to do 34. That's just writing acid dissociation constants. And remember, every one of these is going to be the same. HA plus H2O gives me double-headed arrow, gives me H3O plus A minus. You're going to have to put in the appropriate A, right, for each of those four acids, right? You're going to have to put in the appropriate A. Make sure you put a charge on it over there. All right, so 34, let me see, write these down. I don't know what the heck's going on with Michael and Natalie. All right, so let me write these. So chapter 16, 34. I should give you some on those acid strength and molecular structure that we covered at the beginning of today. Let's see here. Yeah, we could do 36. That's just calculating Ka. So again, you're going to have to set up an ice table for 36. You might want to write that down. Set up an ice table. Let me make sure I'm not giving you one that has a quadratic equation. We don't want to do that. I don't want to have anybody crying over the weekend. All right, so 35 and 36. Let's see here. You know what? Wait, let me see here. Let me see. So do 38, 34, 36. 38 is using that approximation method. And again, go back and look at the example or the one I did on the board, okay? So like 38, there's an exercise that I did on the board that is just like it. So if you're struggling, go back and check. Actually, even if you're not struggling, if I give you 38, you should go back and look in the book. What exercise goes with problem 38, the end of the chapter? And then look in your notebook. Where did Raymond work that problem on the board? Because it's going to be the exact same, just different numbers. All right, so let's see here. 38. And we didn't do the quadratic equation one. I won't give you. Do 42. All right. And then chapter 15, we wanted to look at, so these won't be like word problems. It'll just be saying which one is the stronger acid. So there's only one problem for that. So in chapter 15, problem 52.
Okay.
Yeah, do 52, chapter 15. So what that problem is, so you're given two acids and you're just asked in each case, which one is the stronger acid? All right, in problem 52. Here, I'll tell you this. In 52, you do not have to give the reason. It says explain the reasoning behind your answer. You don't have to do that. Okay, you don't have to do that. So please write that down. 52 with no reasoning. Okay, so again, that was chapter 16, 34, 36, 38, and 42. And then in chapter 15, problem 52 with no reasoning. Okay, all right, why don't we take 10 minutes here? And so I have like 5:18 right now. Why don't we say 5:30? And we'll start the lab. Okay? And I think we can make this work. So everyone has that, the PDF files that I sent you, right? So you should probably open up to, hopefully you read a little bit on that. I told you we were going to be doing that one this class. All right, today. So if you haven't looked at it at all, you should probably spend these 12 minutes doing that. So open up those PDF files, and so we're going to use those in this in 12 minutes. Okay? So we good here?
Is that the lab right up to, or like titration?
Your principal lab.
Okay.
Okay? Because I sent you two of them. One was determination of an equilibrium constant. The other was Le Chatelier's principle. We're doing the Le Chatelier principle one. All right, so there's 5 experiments there. We're going to do 4 of them. All right, and we'll go through them one by one. And well, you'll see once we get started. Okay, so 5:30. All right, so I'll be back in 10 minutes, 12 minutes. I'm going to go wash my hands here. Oh,